Hey everybody, so today we're talking about ideal gases. Now what is an ideal gas? An ideal gas is basically just a gas that the molecules are so far apart that they don't interact with each other. So we can sort of imagine, like, on an exaggerated scale, try and imagine like a container where we have a few gas molecules and they don't interact with each other at all. Now this is just so that like there aren't things going on when we're dealing with the gas. It's ideal, right? So this might not reflect like too much of what goes on in real life. And I have an example problem that I want us to try and tackle here today. And we're going to use the ideal gas formula to figure this out. Now, with the ideal gas formula, you may have seen this written a few different ways. You may see like P V equals MRT, P V equals nRT, P specific volume equals RT. And these are sort of just variations of the same formula, just turned into different things. Now, I believe that like chemical engineers are the ones that deal with this PV equals nRT more, right? Me, myself, I don't really deal with that one. So what I'm going to be using in this online sort of help course is just this PV equals MRT. And this PV equals RT can come about with that. Now, when we're using this formula, right, I can sort of, what happens when I divide through by mass? When I divide through by mass, right, I get P, because that P is still there. I get V, which is specific volume, right, equals RT, because the mass is gone on this side. And remember I said that specific volume is equal to volume over mass. So if you ever see me write that down, that's where that comes from, right? Now, it's important for us to know what these things are. P is for pressure, right? Gases have a certain amount of pressure in them. This V is for volume, right? The volume that the gas is taking up, right? M is for mass. If you guys didn't know, gases do have a mass. No matter how small it is, we have to take that into account here. This R is a gas constant. And this is going to be sort of different depending on what we're dealing with. So like air is going to have a different gas constant than like helium, right? This T is simply just temperature. And it's important to note, as I said, I don't deal with this too much, but in the nRT equation, I believe this R is different from this R. So that's just important to take into account. So that's why we can sort of like sort of switch in between them, because I believe this N is for number of moles. So just keep that in mind a little bit. Now I have an example problem that I want us to tackle here. And this example problem says a 5 cubic meter rigid container is filled with 11.23 kilograms of nitrogen ideal gas, whose initial temperature is 27 degrees Celsius. The nitrogen is now heated until its temperature is 327 degrees Celsius. Now, what I like to do in situations like this is write down my knowns, right? Now, I know that my volume is 5 meters cubed. 5 cubic meters is the same thing as saying 5 meters cubed. The mass is 11.23 kilograms. I have two temperatures, right? So I like to write T1 as my initial temperature, T2, or T1 as my temperature for state 1, and T2 is my temperature for state 2. So T1 is 27 degrees Celsius, and T2 is 327 degrees Celsius. And right off the bat, I like to turn those into Kelvin. When you're dealing with an ideal gas, always convert to Kelvin, right? Now, 27 degrees Celsius. To get from Celsius to Kelvin, we have to, or rather, when you're dealing with an ideal gas, always convert to the absolute. So if you're dealing with Fahrenheit, right, convert to Rankine. If you're dealing with Kelvin, if you're dealing with Celsius, convert to Kelvin. That's what I meant to say. So to get from Celsius to Kelvin, right, we add 273.15. But I personally just round it down and add 273. So 27 plus 273 is 300 Kelvin. They used to say degrees Kelvin, but they changed it at a point in time, and I don't know why. But just a fun fact for you. 327 degrees Kelvin Celsius is 600 Kelvin. right? So now that we know these, we can sort of figure out what we're dealing with here. Now they want us to draw the PV diagram, and they want us to find our initial pressure and our final pressure, right? Now what would the PV diagram for a graph, or PV graph or diagram look for a process like this? Now, I know if you were listening to me earlier, you heard me say, that's our V, that's our P. You heard me say a rigid container, right? What does rigid mean? When something is rigid, it's not moving, right? So this gas is being heated up, and those molecules are like gaining like kinetic energy, and they want to start like pushing on those walls, right? But those walls are not gonna move, right? Normally, naturally, if you push on like, let's say you had like movable walls next to you. If you push, those walls are gonna move, obviously, right? But if those walls are rigid, like this board, right? I'm pushing on that board, but it's not moving, right? So a rigid container just means constant volume, right? Now what is happening in a rigid container when we're heating it up? As I said, those molecules are gaining energy and they want to start like pushing on the containers. And that's a form of like they're exerting more force over the area of those containers. So that's pressure. So that pressure is increasing while the volume is staying constant. So we get a PV diagram that looks like this. And that's meant to be a straight line, right? But am I done? No, I'm not done, because I have to specify my state and the direction, right? So this is state 1, this is state 2, and my direction looks like that. So this just shows that the volume is staying the same while the pressure is increasing, right? So that's what the diagram should look like for this type of process. Now next they want us to find the initial pressure of the nitrogen, right? Now what we're gonna do here is we can use this formula, this PV equals mRT, right? Now what we can do here is we're looking for our pressure, right? So we know that that's unknown, right? Does this V change throughout the equation? I said that no, right? State 1 and state 2 both have a constant volume, right? This M is not going to change either. That mass is a constant. This R isn't going to change either, right? So the only thing that's changing between state 1 and state 2 in this example, right? Well, pressure is changing, but that's what we're looking for in state 1, right? So which T am I going to use? Am I going to use T1 or T2? I'm going to use T1 because I'm looking for the pressure in state 1, right? So we can do this. We can basically say P1 is equal to V times mRT1, right? So I'm going to get this P1 equals V. I'm not going to be writing the units so much since we're getting better with units as we're going along in time, right? This M is 11.23. This R for nitrogen, R is 0.2968. And then that T1 is 300 because we're dealing with Kelvin. Now, what we get when we multiply this through, we get and divide through also, we get we get 199.98 kilopascals, right? And we can just round that to 200 kilopascals, right? So P1 equals 200 kilopascals, right? And you can also say that this P1 is equal to 2 megapascals, right? So I mean it's pretty simple, right? And we sort of do the same thing with the second question when they're asking for the final pressure. We're just dealing with T2 now because it's in state 2. There are only 2 states, so the final pressure would be P2, right? So that P2 is equal to MR, that P2V2, but that V is still the same in 1 and 2, is equal to MRT2. So we get something that looks like this. So P2 is equal to 5. P2 times 5 is equal to M, which is 11.23, times R, which is that 0.2968, which is now times T2, which is 600 Kelvin, right? Now, what we get when we multiply this through, we get, that's 400 kilopascals, about. Rounding is 399.97, but that's 400 kilopascals, which we can say is 0.4. I'm sorry, did I say that, if I said that P1 was 2 megapascals, I meant 0.2 megapascals, because what we do here is we move the decimal place 3 times. So this is actually 0.4 megapascals. 0.4 megapascals. Because 1 megapascal is just, it's 1,000 kilopascals. So just know that. So that's P2, which is 400 kilopascals, which is equal to 0.4 megapascals, right? I mean, so that's really all there is to ideal gases. Just break it down, try and find your knowns, and then what they're generally gonna ask you for an unknown, right? So once you have that, just try and use that to find your unknowns. And you can manipulate this ideal gas formula between that PV equals MRT, PV equals RT, and so on. So I hope you guys were able to learn in this lesson, and please feel free to leave comments in the comment section if you didn't understand anything. Hopefully I can explain it, and please be sure to tell your friends and like it and subscribe. Thank you very much.